Okay, the first part of this week, these 2 weeks are going to be pressure and altitude and density. So pressure is basically just the weight of air. Air weighs so much. If you think about it, uh, the air all the way up through the atmosphere pushing down on you has a certain weight. We measure that weight. We put it in inches of mercury. So for example, if you're at Denver is about a mile high, roughly 5,000 to 6,000 feet. We'll say the pressure there is 24.92. So that is the weight of air. In other words, it's pushing the 24.92 comes from where they used to use mercury barometers. Now they don't use them so much anymore, but it is one measure of it. But say you had no change in air mass whatsoever and you went down to sea level. And sea level was 29.92 as well. So literally 5 inches of mercury difference between the altitude at Denver and the altitude at sea level. So if we wanted to calculate, there are methods to calculate using standard atmosphere and bringing in the current temperature and all. We can get a pressure at sea level. And on a weather map, that's what you're going to see, sea level pressure, because as a meteorologist, I want to know, is the pressure higher here than, say, New Orleans, or is it lower there? So if you look at a surface weather map, bring up one here quick. You can see, for example, here out in West Virginia, the pressure is always on the right-hand side, and this is sea level pressure. So it's 1005.8 millibars. And yes, as a meteorologist, I'm going to deal with millibars. And you might as well get used to it. You're going to see a lot of them. There is a relationship between millibars and inches of mercury, but most of these are in millibars. So that just says that from here, for example, if I went over to Blacksburg, Virginia, there's only a 0.2 millibar difference in pressure between that distance. So there's not a lot, really. And pressure is not, if you look across the changes here, for example, behind the cold front, probably 1,006.1 millibars. We're all the way back here. Here was 1,004 millibars. So a 2 millibar difference. We're getting 5 knots of wind, not very much wind with that. So pressure, really looking at the horizontal, changes relatively small. However, vertical is a whole different story. So let's move along here. And we'll look at vertical surfaces. So here is a 700 millibar chart. 700 millibars is right around 10,000 feet. So literally you had a surface pressure, we'll say, of 1,000 millibars. And within not even 2 miles up, you have dropped the pressure over 300 millibars. We were just looking in 500-mile increments there, literally, and only seeing like 2 millibar difference. So as you can see, the change in the vertical is much, much greater. So there is a huge pressure gradient in the vertical. And when you look at the 700 millibar surface isn't constant. It's just not a flat surface. It's going to go up some, down some. So it would look kind of like this. Here's a low pressure center. Down some. Down this way is high pressure. And these are just contours, literally heights. So this is a sink in the atmosphere there. To get the 700 millibars didn't take as long to rising up through it. If you were flying from here to here, you would be going higher and higher in the atmosphere very quickly, pressure-wise. Even if you stayed at exactly the same elevation, you would be at maybe an 800 millibar level here and a 700 millibar level here if you stayed at exactly the same elevation. So that's one thing I wanted you to get out of this, that pressure change in the vertical is much greater than horizontal. And we're looking at contours on pressure maps in the vertical. So moving on again with some of the pressures here. Here is approximate based on standard atmosphere, what flight level these would be. So 500 millibars, flight level is 18,000 feet. 300 millibars, flight level is 30,000 feet. So you can see the change in pressure in the vertical. These are standard atmospheres. So what they've done is averaged over the course of many, many, many years, atmospheric elevations based on temperature and pressure. Adjustments have to be made to those all time. And I'll tell you now, when you find a day where you actually have a standard atmosphere, it is a rare day. There's always going to be something off with it. So altimeter is what you all fly with, that you want to know the exact altitude you're at. So think about it. If you set your altimeter to 30 inches of mercury and you hit a spot where the pressure is higher, maybe you're going through high pressure than that, so you're actually going to be higher up in the atmosphere at that point than you would be if the pressure was lower. 30 inches of mercury would be a little closer to the surface. So depending on how the surface pressure is varying, you could wind up being higher up or lower in the atmosphere, and significantly depending on how much of a change in the air pressure there is. Another thing to think about is second error is temperature. Maybe not quite as dramatic as that, but if you set your altimeter to 30 here and the pressure air is warm here than the standard atmosphere, you're going to be flying higher. If it's colder, you're going to be flying lower. And there's a reason for that. It's called density. So let's get over to density here for a little bit. Density is basically how many molecules are in a small particle of air. The more molecules in that particle of air, the denser the air is. Well, we talked about temperatures last week, and temperatures making molecules move very fast. Well, now, less colder temperatures, the molecules are moving slower, so you can pack more of them together in a small space. When the air is very hot, the density is much, much less. So maybe you expand those molecules out so they cover a larger area. So if you're taking off, for example, at a Denver airport and the temperature is 100 degrees, it is really hot out there, and you're going to have, effectively, you moved up in the atmosphere to a lower pressure and a lower density, and your aircraft isn't going to perform as well. Now, the same thing if you went up there at that altitude and it was extremely cold, below zero, well, you might be a little below this down in here, and your plane might perform better. So these are things you've got to know as a pilot. That's part of what you're dealing with out there every day. And here's the 700 millibar, but I wanted to show you, we're also starting to talk a little bit about METARs. And we're going to decode METARs. You may already know how to do this. But here's Charleston's METAR. And here's your pressure. It says A right before it. It's the altimeter. So the altimeter is 29.73. So if you were flying in and out of Charleston, your altimeter would be 29.73. Your sea level pressure, on the other hand, is 10,005.6 millibars. The easiest way to think of sea level pressure is if this number, 056, for example, is less than 500, put a 10 in front of it. If that number is is greater than 500, put a 9 in front of it. So if this was, for example, 856, it would be 985. 0.6 millibars, a very low pressure. So that's the easiest way I can tell you, because it's very rare. Only storms like Laura, for example, this last week, have pressures that are extremely low, below a value of 500, below 950 millibars. And Laura only got down to 930 something, I think 934 millibars or something like that. When you're looking at a weather map, and I'm going to show you one right here zoomed in, pressure is always the upper right. We know temperature is over here on the left, upper left. So those are two important values. And for example, today you have a cold front coming through Ohio here, and you can see the pressure drops. See, the isobars kink down around the cold front. The pressure is lower. This is actually the remnants of Laura coming through here, and the pressure is a little lower as well. So in the next section, we're going to talk about winds. Well, I'm not going to go into that right now, but we'll go into winds in a little bit. So hope you got something out of this, and we'll check in with winds here in a minute.